Hey, and welcome back to another LeetCode video. I'm just recording myself practicing for interviews here, and you're welcome to follow along. I'm trying to use the same approach that I used during interviews, where I go through kind of a little system where I first understand the problem, clarify constraint questions, go through examples, explain my approach, my runtime and space complexity analysis before I write a single line of code, and then I'll walk through the implementation or talk through the implementation while I'm implementing it. So this is LeetCode 45, jump game number 2. And we just solved jump game number 1. And this is a greedy problem, but it can also be solved as a dynamic programming problem. And yeah, let's just understand what this is about. So you're given a zero index area of integers nums of length n. You're initially positioned at index 0. Each element nums I represents the maximum length of a forward jump from index I. In other words, if you are at index I, you can jump to any index I plus j where, well, j is between 0 and nums I, and I plus j is smaller than the length of the array. Return the minimum number of jumps to reach index n-1. Test cases are generated such that you can reach index n-1. Right. So my first question to the interviewer would be, how long is nums? Can nums be nil? Are there going to be only positive values, zeros, or even negative numbers in there? Is it guaranteed that there is a solution, or can it be that there exists no solution? What should we return if there is no solution, etc.? And on LeetCode, obviously, the constraints are always listed, so let's just read through them. So the numbers array contains at least one element, and the values are all positive or 0, and it is guaranteed that we can reach the last position in nums. Right. So in jump game 1, we were only asked whether we can reach the end. So jump game 2 now asks us what is the minimum number of jumps that we can take. And yeah, that's obviously why we can solve this with dynamic programming. One way would be to just remember, well, to just compute, how many steps does it take to reach the last position when we start at the last position? How many steps does it take to reach the last position from the one before that, etc., until we reach the beginning, and then we will have, how many steps we need optimally to reach the end, optimally minimum. Right, but a greedy approach should be able to solve this in also in linear time, but with constant space, just like as was jump game number 1. Right, so yeah, let's just look through the examples and see if we can come up with a pattern here. So, and I'm drawing from my experience with jump game 1 for this one. So if we are at index 0, which is where we start, we have the number 2, which means we can either jump 1 or 2 positions forward. So that is what we can reach. And then when we evaluate 3, so what we did in jump game 1 was we kept track of how far can we jump the furthest. And from index 0, the furthest we can jump is to index 2, where the 1 is. So knowing that, we could now say that we're going to iterate over all of the numbers until the furthest index to determine the next furthest index, right? Because that would represent taking a step. So for index 0, we take 1 step into this blue highlighted area. And then we compute what is the next area after the blue highlighted area that we can land into when we go 3 steps. 1, 2, 3, and we can actually reach the end. And turns out the next area is in here, right? So we can reach that area in 2 steps. And now the end is included in that area, on that range, so that we can actually reach the goal in 2 steps, right? I think example 2 looks exactly the same, except for that we have a 0 here, which doesn't change anything, because when we're at index 0, we take 1 step, and then we take 3 steps to reach the end. Okay. All right. Cool. So, well, if we compute the maximum reach for every step, that means we need to be able to increment our index that we use to loop over the array accordingly, right? So if we're at index 0, then we are at index 1, but then we are at index 3. So we're actually jumping over. So I think we need a while loop for that. We'll have, I guess, an index variable I, while I smaller than length of I guess. And then we have to do, well, I represents, well, I gets updated with somehow, but also we need to have a loop inside that loops over all of the elements from position I to the position that we can reach, that we can maximally reach, right? So from if I0, we can reach position 1 or 2. But position I, we can also reach those positions. So yeah, so what we need here is now, I think, another loop from I to I plus however far we can jump. So I think we need another variable for that. Call it max reach, I plus max reach. And since range, the end of the range is not inclusive, we have to add 1 here. And then what we do here is we just increase our I by, no, we have to set it to I max reach plus 1, right? Because we want to set I to the end of the range that we just iterated over. Now in here, we can compute the new max reach. New max reach equals new max reach, and, well, what? Well, the position j plus how far we can jump from j plus nums at index j. 0 here. Right. And actually, we don't have to check, if I is smaller than length num, we can just check max reach, because max reach is always going to be the same or larger than I, right? So yeah, and we have to do a -1 here, because if max reach is actually length of nums -1, that means it reached the last position. Turn result. We now need to count how many steps we took, and result is going to be our step counter. And running this for loop means essentially taking 1 step. Every time we compute a new max reach, that's taking 1 step. Right, and we have to update our max reach, of course, as well, after we've used it here. Right. I think that is correct. Let me just write the time complexity. Obviously, that's O of n, because we iterate over all elements only 1 time. And we have constant space in this, because we're only storing like helper variables. So let's use maybe, I don't know, this example. So when I equals 0, we loop from j from 0 to 0, well, to 1, but 1 is not included in the range. So new max reach becomes 0 plus the value at 0, 2. The new max reach is 2. Now we set I to position 3. No, sorry, to position 1, because old max. So I is now at 3. But we know we can also reach 1 from position 0. We can reach index 2 from index 0. Right, next iteration of the loop, we increase our result counter by 1. Now we iterate from j, or with j, from 1 to 1 plus 2, right? Yeah. So we're iterating over the 3 and the 1. So that what happens is now new max reach is the maximum between 1 plus 3, which is 4, and 0, because that's how it was initialized. So 4 is going to be our new max reach. If j becomes 2, then we take the maximum of 4 plus 2 plus 1, which is this index that we can reach from that index. Or we can reach this index, that index. So our new max reach becomes 4. I becomes max reach for the old max reach plus 1, which is pointing at this one. And then we terminate because max reach already points to the last position. Yeah. So I'm pretty confident that this will work. And let's make a submission. Wrong answer. Okay, so what do we have here? With only ones, we output 2, but we are expected 3. So I think that looks like we have an off by 1 error in somewhere. Max reach, new max reach. Initialize everything with 0. That should be fine. Is it here? Are we breaking up too quickly? Reach. No, that should be correct. For j in range. Oh, I make a mistake here because I plus is the wrong approach. Max reach is already an index. So we don't need to add I to that index, right? If I put nums in here. And if I run this, then we're expected to output 3. And we get the output 3. Okay, so that looks like a bug that we had. Just continuing here. Well, max reach is an index. And so will new max reach will be, which is xj plus the jump distance. Yeah, everything else looks fine. So let's submit this now. And let's accept. Right. That concludes this video.